So, just had a lightning talk. We will now have a thunder talk.
Yes.
And here is Paulette Koronkevich. Go ahead.
Okay, so I'll be talking about Reigniting Fuse, an online partial evaluator for Scheme. Okay, so I should start by saying this is going to be an unusual talk. I'm not going to talk about my own contributions. So you may be wondering, what the heck am I doing up here then? I'm going to talk about a solution to a problem that I found helpful in my own work. It took me a little bit of time to find this work, kind of lost in the tides of time. So it's a bit more like a history lesson, I would say. And so I'm here to reignite that work in a sense. Promise there'll be more puns. Right. Great. So a reason to go back in time is because we need solutions to problems we have in the present. So let me tell you about my problem. So when I was at Indiana as an undergrad, Sam comes to me with this problem. So say we have this small program here, and in preparing it for compilation, we might do something like macro expansion for the Scheme people, or converting it to a linklet, where this small program turns into this giant program, which you can't even read, which was the point. And this ginormous red block turns out to be a bunch of auxiliary definitions that are never used in the original program, which is the tiny sliver there at the bottom. Right. So this is very annoying for our compiler to have to deal with for no reason, really. So the question is, how can we reduce the size of these programs before we compile them? There's a number of ways you can do this. Symbolic execution might be one that you're thinking of, but Sam wanted to explore online partial evaluation. So let's talk about that very, very quickly. I'll go into more details later. But basically, what we can do is we can evaluate this program with all of the information we have at compile time. So in this case, this giant program would reduce to a single value, which is the result of back to 20, which is clearly this number. And with this new equivalent program, we go ahead and continue with compilation. So based on this description, and being an undergrad, I implemented the most naive version of this as possible and found that I was running into infinite loops. So clearly this is a problem, right? And Sam suggested, just timing out, which is a perfectly fine and safe solution, but I was not satisfied with the solution. And so I did some research and found this paper. And this paper presents Fuse, which is an online partial evaluator for Scheme, and presents the termination strategy that Fuse uses, which is going to be the bulk of this talk. All right, so let's get an outline going so we know where we're kind of going with this talk. I'm going to back up a little bit, talk about online partial evaluation and the termination issues that it has. Then I'm going to move on to see what Fuse does to combat these issues. And then finally talk about some, whoa, what just happened? Okay, that was weird. I've never really used this clicker other than the, sorry about that. So don't hit the other buttons, basically. Then we're gonna talk about some counter examples. All right, so let's talk about online partial evaluation. So say we have this small program. Before we even compile this program, it's quite obvious that this evaluates to 7. And not only is this nicer for our compiler to deal with, but even throughout, at the end of compilation, right, we end up with smaller target programs. Another cool thing about partial evaluation is that we can get rid of entire function definitions. So say that this program from before is our entire program. Well, we know that fact of 20 evaluates to this number, so we can just replace the entire program with that giant number, which I will be quizzing you on later, so jot that down real quick. Of course, partial evaluation is not magical, and if we have this factorial call on read, which is an input that we will get at a later point, at compile time we clearly cannot do anything, so we have to return the entire program back. Right, so you might be getting a bit of an intuition for how online partial evaluation works. We're not really going to do any analysis of the program. We're basically implementing an interpreter for this program. And because this partial evaluator is very close to an interpreter, we end up being able to condense our programs quite a bit. So before I continue, I want to talk about the different kinds of values we have at compile time. So we have static values, which are values that are known at compile time. These are like numbers and computations over static values that we know the result of, things like that. And dynamic values are values that are not known at compile time. So this is like function arguments or input we will get at a later point. Right. So the issue that online partial evaluators have is exactly with these dynamic values I just mentioned. So what an online partial evaluator is going to do in this case, when we call fact on this dynamic value x, is it's going to unfold the definition of factorial, replacing every instance of the function argument with x, and then partially evaluated that unfolded call. So as we're partially evaluating this unfolded call, we get to another call to fact, now on sub1 of x. Well, our partial evaluator knows what to do with this. We unfold the definition of fact, replacing every instance of the function argument with sub1 of x, and partially evaluate that. And as we're partially evaluating that, we get to another call to fact, and I could go on forever. I'm surprised you guys let me go on for that long. So a solution to this is, well, when we see a function called a dynamic value, we're just going to stop. And this is a fine solution, and it will work, and it will definitely stop this termination issue, but it's not going to give you the best possible partial evaluation that you can get. So for example, if we have this program, which is exponentiation, very similar to factorial, but now it has another argument, and we only call it on one dynamic argument, we can actually reduce this entire program down to this series of multiplications on this dynamic value, which is something we want our partial evaluator to be able to do. And this is called specialization. We're specializing the definition of the function on the arguments it's called on. Another solution to this might be, as Sam suggested, is time, right? If it's taking too long on a certain function, we're just going to stop. And the problem with this is it can actually increase the size of your program. So say we call fact on a big number, like 100, and our time is up at a certain point during this computation. Well, we actually end up with this expanded program, which is not what we want with partial evaluation. Right, so what do? What does Fuse do? We've got to find a solution, right? So a little bit about Fuse. Fuse is an online partial evaluator for Scheme. As I've mentioned, it operates over programs as if they are graphs, which is not really important. I'm here to talk about the termination strategy. So what does Fuse use in order to terminate on these kinds of programs? It's kind of risky for me to say this at Scheme Workshop, but it uses types. Not exactly types. So the leaves of these programs are symbolic values. And a symbolic value is a pair of a value attribute and a code attribute. So representing the number 3 would look like this. We would have 3 as the actual value and 3 as the code that generates that value. A typical identifier that we don't have any information about would be represented as such, where the value attribute is just value. We don't really know. You can think of this as kind of like a dynamic type, and the code is the identifier. But sometimes we're able to learn a little bit more information about the kinds of values we have. So in this case, maybe from the context, maybe we use this in a plus expression, this identifier b. And so we would have nat as the value attribute and b as the code attribute. Just to emphasize, the person writing the expressions does not actually have to include these types, but Fuse kind of has this pass over the program to learn these. Right, so recall that the problem we're trying to solve is we want to be able to specialize our programs on the arguments that they're called on, but we don't want to take it too far because we end up in these infinite loops. So the way that Fuse prevents this is using a specialization cache. So when we call fact on this dynamic value that we know somehow is a nat, we go ahead and note in the cache that we've called fact on this nat, right? We index the cache by the value attribute of the arguments. And we do, as we do normally, just unfold the call and partially evaluate that. And we encounter another call to fact, again on a nat. And this is where our cache tells us to stop, right? Because we haven't learned any new information about the arguments we're calling it on. And so it's still a nat, as you can see in the value attribute. And so we find this entry in the cache and stop. So a little bit more detail here. we call fact on this X. We go ahead and note that in the cache. We unfold the call to fact and find this call to fact again on this NAT. We look up the NAT and find that in the cache. So that's this is the end program we have here. I've kind of deleted the symbolic value here. What about our exponentiation example? Well, we have these two arguments, x and 3, which is a NAT and 3. So we go ahead and put that into our cache. We unfold the call to exp. We find another call to exp. We look up these arguments, but don't find them. So we go ahead and put those in the cache. And as we keep going, we add another entry to our cache and eventually get down to this program. So yay, we solved this problem. Now let's talk about some counter examples. OK, so this is kind of a fancy factorial definition. It's not unusual, though. So this factorial uses an internal loop. And this loop is called on two values right off the bat, 1 and 1. The two arguments are, one is a counter, and the other is the accumulator. And it's tail recursive, and overall, not an unrealistic program. We want our partial evaluator to be able to handle these kinds of programs. But I want to bring your attention to this, the termination the condition. Thank you. The termination condition of this function is reliant on the first argument to fancy fact. Right? So our call stack kind of ends up looking like so. And our cache is growing forever. And so our specialization cache is not going to help us in this case. And obviously, online partial evaluators don't do well in these kinds of programs. But it turns out that offline partial evaluators, which use some fancy techniques in order to detect possible infinite loops, also fail on these examples. So what does Fuse do? Fuse uses another cool PL technique, abstraction, which in the paper is described as online generalization. Right, so Fuse also maintains the stack of active function calls. Right. So here we have the definition of factorial, and we call it again on our classic example of a dynamic value, x. So we go ahead and put that call on the stack. Then as we're evaluating the call to fancy fact, we encounter another call to a function. This time it's called loop. And then as we're evaluating loop, we make sure to note on the stack that we've encountered a conditional of which we don't know whether we take the true or the false branch. And this is very important for the online generalization algorithm. So we make sure to note that on the stack. And as we're evaluating both branches of this if statement, we encounter another call to loop, which we promptly add to the stack. And this is where our online generalization kicks in. We notice that there are two calls to loop on different arguments with this conditional marker between them. So we abstract the arguments that it's called on. In this case, we're calling it on two nats. So we go ahead and abstract those two arguments to be of type nat and also just to be an identifier. And now we evaluate the call to loop with respect to these abstracted arguments. And as we're evaluating this call to loop now on these abstracted arguments, we encounter another call to loop, again on two nats in this case. And this is where our cache goes ahead and tells us to stop. So this is how Fuse can detect these kinds of loops that contain kind of static values under dynamic control. Right, so if you're interested in implementing an online partial evaluator, but find that you're running into infinite loops, have no fear, Fuse is here. You too can prevent partial evaluation loops using a specialization cache and online generalization. And here's the paper again for reference. Thank you very much.
Questions?
Leaf?
So, okay, maybe this technically doesn't terminate. How big are the residual programs?
That is a great question. Thank you. I was hoping somebody would ask. So Fuse actually, if we go back a little bit to the specialization cache here, you can actually notice that this residual program is bigger than our original program, which, what was this all for, right? And actually, Fuse has this technique of rolling this back up So whenever we hit something in the cache, it actually can detect the previous call. So it'll actually end up being the original call there. So they shouldn't be any bigger.
Okay.
That is the goal.
So are you using this for something then, or are you?
Yeah, that is the confusing part of this talk. Yes, I used it in my own partial evaluator. So I was writing a partial evaluator for Racket's linklets and found this problem and then found this paper. So I kind of re-implemented it for my own partial evaluator.
Okay, cool.
Did
And
you
it-
find out what Daniel Wise has done since that paper?
I am very curious, but I have not found it.
This program evolved into the largest scheme program ever at Microsoft Research, and it was extremely difficult to find computers on which you could run this program. So Daniel was
Fuse itself evolved into?
the analysis part of Fuse became the analysis part that Daniel Weiss did for Microsoft C++ code base. And he would teach people how to use Emacs and this program remotely on a computer far away for the C++ programs, and they hated Emacs. Can you imagine that? So that's why it failed, and that's why Daniel Weiss turned into split this program up into a tool for C++ called parsers that would find bugs, bug finding tools, and it would became the standard in 2002 after Microsoft managed to strand an aircraft carrier in the Atlantic Ocean.
Wow.
And then he retired, right?
And then he retired.
So that's your question. Then was retired.
But it's because his brother was the vice president, he didn't make it that far.
Yeah. But I remember that they were shopping around for, which was unheard of at the time, is for a 64-bit machine
Yep.
to run Fuse.
They couldn't run it.
So this was 90,
Wow.
90 something. Yeah.
I thought the M64 was out then.
But it was just that not very many people had one, right? So
This is great. Thank you.
yeah.
That's why I went there.
Time for more questions?
Oh, yeah, we have plenty of time.
So I was a little bit confused.
Oh, yeah.
So it sounded like if you have a dynamic condition on the stack, then you do some sort of
Sorry, a lot of,
you
yeah.
lose
Yeah, this-
precision in the cache entries.
yeah.
So does that mean that if you have just an unconditional infinite loop,
Yep.
then it'll just say,
Keep on going.
I still know the number, I'm
Yep.
gonna keep going.
Yeah,
Okay.
yeah. They brought this up later in the paper. I can't recall exactly what they did, but they couldn't find like a good heuristic for detecting those kinds.
Okay. So if you have the bad judgment to run
Yep.
this on a true infinite loop of a
Oh,
certain
yeah.
kind, then you just deserve
Yep.
whatever happens.
Yep. Pretty much.
So that reminds me a bit of the kind of PC tainting that information flow does, but I don't know if there's any interesting connection there.
I'm not sure. There could be.
Okay. Anyone else? Okay. Thank you very much.
Thank you.